Hello everyone, welcome to the Intro to ANT breakout presentation. My name is Nathan Schleppe and I work on the device-to-device connectivity team here at Garmin, and I'm excited to be presenting to you on ANT today. This presentation will be broken into 4 major sections. The first section will be a crash course on ANT. In this section we will go over what ANT is at a high level, then jump down into some of the finer details. By the end of the section, I am hoping to give you a solid idea of what ANT is and how you can leverage its many features to start solving your customers' problems. The next 2 sections will go over 2 prominent applications of the ANT protocol. At a high level, ANT Plus is a managed network that allows devices from different manufacturers to talk to each other and solve problems, primarily in the fitness and wellness sphere. ConnectIQ provides developers with ANT and ANT Plus APIs so that you can easily harness the power of ANT in your ConnectIQ applications. Finally, this breakout session will be concluded with a Q&A. ANT Crash Course. This section is a condensed version of the ANT Basics presentation given in years past at some other conferences. There's a lot of content, but it should be enjoyable if you find stuff like network topologies, serial interfaces, device power consumption interesting. If you have any questions, please write them down and ask away at the Q&A. So what is ANT? Anyways, at a high level, ANT is a wireless sensor network protocol operating on the 2.4 GHz ISM band. ANT is an ultra-low power protocol designed for personal area networks. ANT is capable of operating with power consumption in the range of milli or even microamps. This means that ANT is a great solution for devices that are meant to last for months or even years on a coin cell battery. ANT is also compact and highly optimized, designed for systems that are resource constrained, which is often the case in the embedded world. Low-level security features are built in. Finally, ANT is flexible and scalable. It supports many different network topologies, including peer-to-peer, broadcast, and star. Connections can be transient or maintained over long periods of time. You can find more information at thisisant.com. There are many different ANT components available for a designer to choose from in the form of chips, chipsets, modules, and SoCs. Which component a designer should choose depends on factors such as cost, power consumption, complexity, and multi-protocol support. Designers who want to integrate ANT into their product should check out the Nordic NRF52 and NRF53 line of SoCs, as well as the soft device packages. More information about this can be found on the Nordic website or at thisisant.com. To date, ANT can be found in hundreds of millions of devices worldwide for a variety of use cases. For example, ANT is used to connect heart rate straps and other sensors to wearables and collect data for fitness leaderboards. ANT is also available for developers to easily harness through a ConnectIQ SDK API. Stay tuned because we will be talking about this later in the presentation. Okay, so we've talked about ANT at a high level and established some of the possible use cases. The next several slides are going to do a deep dive into how ANT works and explain how some of the various ANT features can be used to build a solution for your specific use case. First, we will be defining an ANT node. An ANT node consists of a host and ANT protocol implementation, often separated by a serial interface. In the case of SoCs, the interface to ANT is handled via libraries. The ANT protocol engine handles the complexity of establishing and maintaining ANT connections. The host handles the particulars of the application. Next, we will be defining an ANT channel. ANT channels are a fundamental building block of the ANT protocol. They connect 2 or more nodes together and can be thought of as the pipe that allows data to be passed between nodes. At minimum, each channel must have a single leader and follower participant. The primary direction of data flow is from leader to follower. A single node can act as both a leader and a follower participant simultaneously. ANT uses a TDMA channel access method, which means that each channel exists in its own time slot, which repeats periodically. A leader will always transmit a message on each channel time slot. If the channel is bidirectional, the follower may optionally transmit a message back. Note that ANT has built-in mechanisms that prevent it from interfering with open channels from other devices. How this is accomplished is beyond the scope of this session. All you need to know is that ANT is designed to support many different channels in the same RF space at the same time with very little to no effort required from the designer. It can also coexist with other wireless protocols like BoE or Wi-Fi. So far, we have covered how a channel can be thought of as a data pipe that connects two nodes together and is open periodically. But what differentiates one channel from another? If there are many devices in a room, how does a wearable that displays heart rate data know it is connecting to a heart rate sensor and not a cadence sensor? How does the wearable differentiate between two different heart rate sensors in the same room? ANT channel parameters solve these problems and more. The first channel parameter we'll be talking about is channel type. Channel type specifies the type of communication that will occur on the channel. Most ANT channels are independent and bidirectional. An independent channel is used to create the peer-to-peer and broadcast network topologies. That is, one leader node sending data to one or more follower nodes. A bidirectional channel means that data can be sent in both the leader to follower or follower to leader directions. A shared channel is used when a single ANT node must receive and process data from many nodes. On a shared channel, multiple nodes share a single independent channel with the central node. As an aside, another option to consider when designing a system where a single node must receive data from multiple nodes is continuous scanning mode. In continuous scanning mode, a node opens a channel that listens all the time for broadcasting leader nodes. This option will allow for higher throughput for each leader node, but the node with continuous scan mode enabled consumes a lot more power. The next channel type is RF frequency. This is the frequency that the ANT channel operates on. ANT supports 78 unique RF frequencies in the ISM band. A large number of channels can coexist at a single RF frequency. ANT Plus devices, as we will discuss later, operate primarily on the 2457 MHz band. There can be many ANT Plus devices in the same RF space without interference. It is not recommended to use a 2457 MHz band for non-ANT Plus devices. It is the product developer's responsibility to ensure that RF frequencies used will comply with the regulations of all regions of the world in which this equipment is to be used. The channel ID is the most basic descriptor of a channel and can be broken up into three different components: transmission type, device type, and device number. The transmission type specifies the channel's channel type. Recall that this can be either independent or shared, and whether common data pages are used. It can also be used to extend the device number from 16 bits to 20 bits. This is called the extended device number and can be used to reduce the probability of two devices having the same device number in the same space. The device type is used to specify the class of device. For example, a heart rate sensor versus a speed sensor. The most significant bit is a pairing bit, which makes up part of one of ANT's pairing mechanisms. The device number is meant to uniquely identify a device from other devices with identical transmission and device type. For example, differentiating between two different heart rate sensors. Leaders cannot set the device number to 0x0000. The channel period controls the basic message rate of data packets sent by the leader. It can be used to balance throughput requirements with power consumption requirements. As the channel period decreases, throughput increases, but power consumption also increases. Finally, the network key channel parameter is used to uniquely identify a network. The network key can provide a level of security and access control. Only channels with identical, valid network keys may communicate with each other. A network can be used to specify a set of operating rules for all participating nodes. A managed network defines rules and specific behaviors governing its use. This allows products from different manufacturers to be interoperable. As we will see later, ANT Plus is one such managed network. As a quick tip, make sure that you set the correct network key for your device. For security reasons, ANT will always return a success response, even if you entered an incorrect key. Okay. So now that you know what a channel is and how it can be configured to meet your specific use case requirements, you may be wondering about how data is communicated across ANT and the features available to transmit different types of data. This is where data types come in. There are three main data types supported in ANT: broadcast, acknowledged, and burst. Bidirectional channels are not restricted in which data type they can send. Each of these data types can be sent in either the forward or reverse direction at the discretion of the host implementation. Broadcast data is the most basic data type and is transmitted by default if no other data type is specified. The broadcast data type uses the least amount of RF bandwidth and system power. The downside is that the node where the data is transmitted from will not be aware of any dropped packets. This makes broadcast data the preferred choice if occasional data loss is accepted. For example, a sensor that transmits outdoor temperature. The next data type is acknowledged data. When a node receives an acknowledged data packet, it will respond back to the originating node with an acknowledgement message. This feedback allows the originating node to retry sending a page if necessary. This mechanism does result in higher RF bandwidth and power consumption. This data type is ideal for transmission of control data, where each node needs to be aware of each other's state. Note that ANT does not automatically retransmit unacknowledged data packets. This must be implemented by the host. Finally, we will discuss the burst data type. Bursts are designed to transmit a large amount of data between devices. Bursts are capable of throughput between 20 to 60 kilobits per second. In general, it is best practice to limit the amount of data sent using the burst data type at one time. Bursts can interfere with other devices operating at the same RF frequency, and excessively large bursts can start other channels operating on the node, as well as cause a loss in synchronization between nodes due to clock drift. Bursts also have the highest RF and power cost. The last topic we will be going over in this section of the presentation is device pairing. In ANT, pairing involves establishing a relationship between two nodes that wish to communicate together. To pair, a follower node acquires the unique channel ID of the leader node. ANT provides a lot of flexibility in the pairing process. Connections can be permanent, persisting across drop connections and device power cycles, or transitory, where the connection only lasts for as long as the follower device needs to be connected. There are also several built-in mechanisms designed to facilitate pairing across a variety of use cases. These include the pairing bit, inclusion-exclusion lists, and proximity search. A leader's channel ID is broadcast with every message. Recall that the channel ID is made up of the transmission type, and device number. When a follower's channel is opened, it has a couple options for how to set its channel ID. If it knows the channel ID of the channel it is trying to connect to, it can set its channel ID to that ID and begin searching. If, on the other hand, the follower does not know the exact channel ID of the device it is trying to connect to, it can use a wildcard search. A follower can wildcard any of the channel ID fields by setting them to 0. So, if, for example, the device is trying to search for a heart rate sensor, but the device number is not known, the device type can be set to the heart rate device type, but the device number can be set to the wildcard value. So, you've been listening to me talk about ANT for a while now, and you are probably starting to wonder if there are any tools available that will let you try some of this out. It turns out there is, and it's called Antware. Antware is a PC application used for the control of ANT wireless devices. It is a great tool if you want to experiment with any of the numerous ANT capabilities. Tasks such as configuring a channel, pairing, and logging a data stream are easily accomplished using Antware. Antware also supports a basic scripting language to make automation of tasks easier. To use Antware, you will need an ANT USB device. For the remainder of the presentation, we will be talking about a couple ANT applications. The first is ANT+. Not to be confused with ANT, ANT+ is a managed network built on top of ANT that allows devices from different manufacturers to communicate in a defined and interoperable way. ANT consists of a collection of device profiles, each designed for a specific use case. Device profiles are usually designed for use cases in the sport, fitness, and wellness spaces. ANT+ is also a brand. Devices that want to talk ANT+ are required to go through a certification process. ANT+ branding on a device means it has been certified to be interoperable with other ANT+ branded devices. The ANT+ Alliance is an open special interest group of companies who have adopted the ANT+ promise of interoperability. You can join the ANT+ Alliance as an ANT+ adopter for free and get access to the ANT+ network key, as well as access to device profiles, simulators, reference code, and technical support. If you want to get a little bit more involved, consider signing up as an annual member. As an annual member, you get access to device profile technical working groups, or TWGs for short. TWGs are used to create and maintain ANT+ profiles. They are made up of member companies with a vested interest in the profiles being discussed. More information about ANT+ can be found at thisisant.com. Even if two devices are using ANT, they may still not be able to understand each other. ANT+ leverages the network key and device type channel parameters to solve this problem. If you recall from the ANT crash course, the network key is used to uniquely identify a network. ANT+ is a managed network. meaning it has its own unique network key and there are defined rules and behaviors governing its use. The device type field is used to differentiate between different types of ANT+ devices. Each device type has its own device profile, defined with specifications designed to allow devices to understand each other, even if the devices are made by different manufacturers. To sum up, a device can easily check if another device is ANT+ and what type of ANT+ device it is, simply by checking the channel parameters. As previously mentioned, device profiles are a specification that, when followed, allow two different ANT devices to talk to each other. Given how fundamental they are to ANT+, I want to take some time to go over the basic anatomy of a device profile. Complexity varies across profiles, but in general, there are three basic elements that make up a profile. These are channel parameters, data pages, and transmission pattern. We went over all the channel parameters in the ANT crash course. For each ANT+ device profile, a specification exists explaining how to set each parameter. Some parameters are specified by the ANT+ network and are the same across profiles, and others are unique to a specific profile. Others still are unique per device or manufacturer. Care should be taken to understand and set each parameter correctly for each device profile implemented. Of note, it is important to remember that the device number cannot be set to reserved value 0x0000. Manufacturers are also responsible for ensuring that each production device has a unique device number. One way of doing this is by creating a relationship between device number and the lower 16 to 20 bits of the device serial number. 8 bytes of application data can be encoded each time a message is transmitted over an ANT channel. ANT+ device profiles specify encodings for this data. In ANT+, the first byte of each data message is always the page number. The encoding for the remaining 7 bytes changes depending on the page number. Together, we get is referred to in ANT+ as a page. There are 256 available pages in most profiles. Available data pages are broken up into 3 primary regions. Profile-specific data pages are unique for each profile. Common data pages carry the same definition across all profiles. Manufacturer-specific data pages are not defined by the profile, and each manufacturer with a unique manufacturer ID is free to create their own definition. Manufacturers that are ANT+ annual members are free to request an ID using a form found on thisisant.com. This slide shows an example profile-specific page from the heart rate monitor profile. The definition is for the default page. The page number is 0 and it is encoded with the heartbeat event time, heartbeat count, and computed heart rate fields. The last basic element of a device profile is the transmission pattern. Specifying transmission patterns ensures that each implementation of a profile is meeting certain data and throughput requirements. In general, there are 2 sub-transmission patterns working in a device profile. The main page pattern transmits data that has low latency requirements. For example, data pages that contain user, heart rate, or speed data. The background page pattern is designed for data that has low latency requirements. An example background page would be the manufacturer information page. This page contains information about the device manufacturer and will not change on the device. Often, there is a need to retrieve information from a background page immediately on connection. To accomplish this, devices can make use of the request data common page. This page allows a device to request that a data page be immediately transmitted across the channel. If you want to experiment with or test ANT+ devices, Simulant Plus is the developer tool of choice. Simulant Plus is a PC application used for simulating ANT+ devices and displays. It is an excellent tool for first-time ANT+ developers to simulate a sensor or display. It is also invaluable in testing products to ensure that they meet device profile specifications. This tool includes a Python-based scripting framework that can be used to automatically test many of the device profile requirements. To use Simulant Plus, you will need an ANT USBM device. ANT+ product certification is a service administered by ANT Wireless and involves ANT and ANT+ communication capability verification, ANT+ device profile implementation testing and review, and an ANT+ brand review. Certified products receive many benefits, such as product listing in the ANT+ product directory, approval to use ANT+ logos, icons, and word marks on their product and product collateral, and certification reports. Most importantly, ANT+ certification helps ensure that your product will be interoperable with other ANT+ products in the ecosystem, including Garmin devices. Any product or application that incorporates ANT+ technology and is sold or made generally available must be certified. To get started with certifying your product, head to thisisant.com. As the markets that ANT Plus devices operate in continue to advance and evolve, so too should the device profiles that support these markets. We strive to update profiles with feedback and proposals from partners. If you have an idea on how to make a profile better, reach out and let us know. The second and final ANT application we will be talking about is ANT and ANT Plus in Garmin Connect IQ apps. Connect IQ is a development platform maintained by Garmin that allows third parties to create unique wearable experiences for their users on Garmin devices. With Connect IQ, developers can leverage the sensors and features available on a Garmin device, like UI design, location, web services, and power management. These tools can be used to create watch faces, widgets, data fields, and more. The Connect IQ platform consists of the Monkey C programming language, the Connect IQ SDK, and development tools, and the App Store. Connect IQ apps are developed using a language called Monkey C. Monkey C was designed for easy app development on wearable devices. If you are familiar with dynamic languages like Java, PHP, Ruby, or Python, Monkey C should feel very familiar. Developers can make use of the Connect IQ SDK to support apps and can distribute them on the Connect IQ store. If you are interested in learning more about Connect IQ and all the features it has to offer, I would encourage you to check out the API documentation online, which can be found at developer.garmin.com/connectiq. For this presentation, we will be focusing on how to hook your Connect IQ apps up to ANT and ANT Plus using the ANT APIs. There are two different Connect IQ APIs that let you leverage the power of ANT in your application. These are the ANT and ANT Plus APIs. We'll be starting with the ANT API. The ANT API provides the most amount of flexibility, allowing a developer to access all the lower-level features required to implement a custom solution. This includes the ability to set all the channel parameters we talked about in the ANT section of this presentation, receive events directly from the radio, and send broadcast, acknowledged, and burst messages across the channel. A developer may also want to consider using the ANT API if they are trying to make use of an ANT Plus profile that is not supported in the ANT Plus API, or if the profile is supported, the API does not expose a certain aspect of the profile. Over the next few slides, we will be working through a small code snippet which shows some of the more important aspects of the ANT API. This first slide highlights an ANT Plus heart rate sensor inheriting from the ant.generic channel class. You can think of the generic channel class as the gateway between your application and the ANT radio. With it, you can specify your channel's channel parameters, open and close a channel, and send and receive messages from the radio. Next, we will talk about setting up the channel. There are two stages to this: channel assignment and device configuration. For channel assignment, you first specify the channel type and network key for the channel using the channel assignment structure. You then attempt to acquire the channel by passing the structure to the generic channel constructor. Note that a radio only supports a set number of channels. If you try acquiring a channel but there are none available, an exception will be thrown. Also, don't forget to call the release method when you are done using the channel. This will free up radio resources for other applications to use. Device configuration involves specifying the remaining channel parameters. This includes parameters like transmission type, device number, and channel period. If you are trying to implement an ANT Plus profile, don't forget to check out the profile documentation to make sure you meet channel parameter requirements. Finally, you need to set up a callback so that you can receive messages from the radio. The callback is initialized by passing it as an argument in the generic channel constructor. While your application is running, you can expect most messages to contain application data in the form of a broadcast, acknowledgement, or burst. There are additional messages you will need to handle as well. For example, if you have set up your channel as a follower, you will have to handle events related to losing connection with the leader or not being able to find one in the first place. More details about radio messages can be found in the API documentation. One last note, if you want to send application data across the channel, you can accomplish this easily using the generic channel classes sendBroadcast, sendAcknowledge, and sendBurst methods. While the ANT API provides developers with a lot of flexibility to set up their channel and send and receive messages as they want, there may be cases where hooking into an existing ANT Plus implementation would suffice. This is where the ANT Plus API comes in. The ANT Plus API allows developers to easily hook into existing ANT Plus profile implementations and start receiving data. All the work of setting up and maintaining a channel happens behind the scenes. As you can see on this slide, there are several profiles supported. The next slide will show you just how easy this is. All of the specific ANT+ device classes, such as bike cadence shown in the slide, inherit from the ANT+.device class. Using the device class, you can access common types of information such as sensor battery status, manufacturer information, and product information. You can also send messages using the device class. For example, you can send a data page request to a sensor. This is useful if you need access to information from a sensor immediately without having to wait for it to be sent in the transmission pattern. You can also send manufacturer-specific information pages. If you recall from the ANT+ section of this presentation, manufacturer-specific data pages are not defined by the profile, and each manufacturer is free to create their own definition. Hooking your application up to a sensor is easy using the ANT+ API and only requires a few lines of code. In general, you have two options for how to receive data. The easiest way is to pull for the data. In this case, all you must do is create an ANT+.bytecadence class instance and call the get method for the data you want. In this slide, we are calling the getCadenceInfo method. The second method is event-based. For this method, you first create a listener class implementation that extends the profile listener class. On the slide, we are extending the bytecadence listener class. You then pass an instance of this listener into the device constructor and you are good to go. You can find an example listener implementation in the ANT+.bytePowerListener API documentation. If you are planning on integrating ANT+ into your application, be aware that it may need to be run through ANT+ certification before it is released. If you're using the ANT+ APIs, there is no need to certify. However, if you are implementing an ANT+ profile using the ANT API, you will need to get your application certified. For ConnectIQ apps, certification is free of charge. Don't worry, we're not going to leave you hanging with just the code snippets in this presentation. You can find an example project available in the Garmin/ConnectIQ apps GitHub repo. There are two components to the project in the repository. The first is a monkey barrel. You can think of this as a reusable code module that uses ANT API to implement a basic ANT+ heart rate display. The second is a data field project that uses the monkey barrel to connect to a heart rate sensor and display heart rate to the user. The ConnectIQ SDK also provides several development tools to aid you in testing your application. There is a unit testing framework as well as a device simulator where you can test your application on a bunch of different Garmin products. The simulator will require an ANT USB device plugged into your computer. You can also use the Build for Device wizard to build a version of the app that you can sideload onto a real device for testing.